Okay, yeah, thank you, Matt. Yeah, let the series A sub n and B, the series of B sub n are series with A sub n, B sub n positive. Okay, now if the series Bn is convergent, I think I want to say n, A sub n less than equals to B sub n, then the series A sub n is also convergent, because the idea is basically is the following. We have this, right? Okay, so the summation will also have this situation. Now, if this is convergent, then this must be convergent. Okay, if the upper bound is convergent, then the one you have below is also convergent. Okay, on the other hand, if the smaller series is divergent, okay, and if it is divergent, it will diverge to infinity, by the way. Okay, if it is divergent, it will diverge to infinity. Then the upper, the greater series will also be divergent. Okay, now some little details. If you go through the proof, the details will be as the following. Let's say this is convergent. Let's say this is convergent to a number k. Let's say that's convergent to number k. So this series A sub n is bounded above. Right? Is bounded above. That's one. Second, the nth partial sum is increasing. Why? Because you keep on adding positive terms. Right? The series, the nth partial sum, form an increasing sequence. So what happens is S1 is less than S2, less than S3, less than S4, so on and so forth. Okay, but at the same time, it will be bounded above by K. Right? So by monotonic sequence theorem, this sequence here, the sequence of the series, will be convergent. That's the reasoning. Okay, now using the same reasoning, you will see that the second part, if it is divergent, it will diverge to infinity. Why? Because it's positive term. Because it's positive term. You can only increase. Right? You can only increase. So the n partial sum here is increasing because the sequence is positive. Right? Now, if it is increasing and becomes divergent, it can only increase to infinity. Okay, that's for the comparison test. Now, the second part is a more interesting one, the limit comparison test. The limit comparison test. That says let the series for A sub n and the series for B sub n are series with positive terms. if A sub n over B sub n, the term by term ratio converges to C, which is positive n finite, then both the series, I should say, the series A sub n and the series for B sub n are both convergent or both divergent. Okay, now we usually use this limit comparison test if comparison test doesn't work but very close. Like for example, this one here, for example, 1 over n, the series of 1 over n is harmonic. So we know it's divergent, right? Okay, that one we know. Now, the thing is, if we have the series of 1 over n minus 1, for example, and the n start from 2, you may argue that 1 over n minus 1 is greater than 1 over n. Is it right? And therefore, this series here is divergent. So this guy is also divergent. Does it make sense? Okay, you can just use comparison test. Now, the thing is, it doesn't work if I make it plus here. The series of n 1 over n plus 1 is actually smaller. It's actually smaller than 1 over n. Right? But bounding it above by something divergent doesn't give us any conclusion. You see, binding it above by something convergent, something divergent does not give us any conclusion. Now, in that situation, then we see, oh, you know what? If I do the ratio 1 over n plus 1 over 1 over n, this is n over n plus 1. This is 1 over 1 plus 1 over n, but this converges to 1, which is positive and finite. That's the limit comparison test. Okay. Now, this section is based on these two tests. Either you do comparison or you do limit comparison tests. Okay. Now, let's see. I wonder up to what problem did I do last time? I don't think I did a lot of problem last time. Let me see my notes. 262, 11.4a. I did up to number 17. 7, 3, 7, 9, 17. Do you have any problems you want to do from here beside those? Let me randomly pick number 15, for example. Okay, the series from 1 to infinity of 4 to the n plus 1 over 3 to the n minus 2. Notice that solution for n greater equals to 1, we see that 4 to the n plus 1 over 3 to the n minus 2 must be greater than 4 to the n minus 1 over 3 to the n. Why? If you divide by something smaller, the quotient will be greater, right? Okay, to be safe, let me make it equals to, greater or equals to. But that means this guy here is 4 times 4 over 3 to the n. Okay, so the series, and this is positive, by the way. This is positive for n greater than 1, greater or equals to 1. So the series from 1 to infinity of 4 to the n plus 1 over 3 to the n minus 2 will be greater or equals to the series, okay, of 4 to the n plus 1 over 3 to the n, which is equals to the series 4 times 4 over 3 to the n, right? Now, what can you tell about the series on the right-hand side? But that series, be explicit. You are talking about 2 different series right now. Okay, so you need to be explicit. You cannot just say, oh, the series is divergent. Which series are you talking about? Okay, so be explicit. So this series, but this series here is what kind of series? Is geometric with r equals to 4 over 3, which is greater than 1. So this guy is divergent, right? Now, then you go back. It's bound this divergence positive series, bound the series we are observing below by the comparison test. Or you can just say CT. This series 4 to the n plus 1 over 3 to the n minus 2 is divergent. Okay, that's for number 15. Let's see number 21. I think that one is harder. Number 21, we have the series from 1 to infinity of square root of n plus 2 over 2n squared plus n plus 1. If you try to use comparison, this guy is greater than this. Okay, but this guy is smaller than this. You see what I mean? So it can go both ways, and we don't even know if either one of these is convergent or divergent. Now, if you have too many terms like that, one thing you can do is use limit comparison test instead. Okay, now think of it this way. Notice that the degree on the top is degree of 1/2 square root of n. Degree of the bottom is degree of n squared, right? Degree of 2. That's what you will compare that with. Now, the thing is, this guy is a p-series, actually. That's p equals to 3/2, and therefore it's convergent, right? Okay, so I will use limit comparison test against that blue part. Now, the one in blue is just what I have in my mind, though, or on my scratch paper. Now I need to show the work formally. Okay, let A sub n be the terms, the sequence square root of n plus 2 over 2n squared plus n plus 1. And the sequence b sub n is square root of n over 2n squared. So a sub n over b sub n is equal to, I will multiply by the reciprocal, okay, times 2 square root. Actually, I don't need that 2. I don't need this 2 here. You can use that 2 if you want. This is equal to n squared over 2n squared plus n plus 1 times square root of n plus 2 over n. Okay, and this is equals to, now for the first factor, I will divide by n squared. And this one here will be 1 plus 2 over n. Now this will be convergent to 1 over 2 plus 0 square root of 1 plus 0, which is positive and finite, right? So by limit comparison test, oh, you know what? I need to first say that the series b sub n. Now, the series from 1 to infinity of b sub n square root of n over n squared is equal to the series 1 over n to the 3/2 is convergent by p series. So you need to first argue why the series you used for comparison is convergent, okay, by p series, p equals to 3/2. And the reasoning is usually simple, right? You know it already, but not, you cannot say, oh, but that's obviously convergent, Thomas. You need to tell me why, okay? Now, by p series, the series for b sub n is convergent, okay? Then, by limit comparison test, the series for a sub n, which is the series square root of n plus 2 over 2n squared plus n plus 1 is also convergent. How about number 31? That's interesting. I see that question, especially they mark it in red. Let's talk about that a little bit. Infinite series of sine of 1 over n. Notice that when n goes to infinity, then 1 over n gets very, very close to 0, right? And sine something very close to 0, sine blah, when blah is very close to 0, is congruent. It's behave very similar. No, I don't want to use this notation. I want to use this sine. So what I write in blue is what I have in my mind. Sine 1 over n works similarly to 1 over n when 1 over n is very close to 0, which means n is very close to infinity. Okay, so what I think I will do, I will compare that with 1 over n. Okay. Let a sub n be sine 1 over n, and b sub n is 1 over n. By the way, make sure that the series is actually non-negative though. Okay, make sure it's positive. Now then, a sub n over b sub n will be sine 1 over n over 1 over n. Oh, shoot. Oh, I need to use limit notation now. Why, Thomas? Well, because I plan to play with the limit notation. I need to play with the limit notation. Move it a little bit to the right, insert the limit. But that means limit 1 over n goes to 0 from the positive side. Okay, use dummy variable t, for example. And I don't use L'Hopital rule here. I'm just using the fact that sine t over t as t goes to 0 is 1, which is positive and finite. Okay, now the series for Bn is a harmonic series, therefore it's divergent. So by limit comparison test, the series a sub n is the series from 1 to infinity of sine 1 over n is divergent. Okay, that's for number 31. That's for number 31. Any other question you want me to work on? Nothing. That's basically it for this section. Let's think about, before I go on to the next question, let's think about number 43. I don't know that question. I don't know that question. I mean, I don't know how to do that one yet. Okay, but the question is show that if we have the series to be, I mean, the sequence is positive sequence, and n times a sub n converge, not converging to 0, then the series a sub n is divergent. If n times a sub n not converging to 0, then the series a sub n is divergent. Proof. So n a sub n is equal to a sub n over 1 over n. Now this is not convergent to 0, but I don't need it to be 0. Oh yeah, if it is not 0, we need number 42 to answer this question. Or is it 42 or 40? I'm trying to say this. If this is not converging to 0, so it's either converging to a finite number, positive, or to infinity. Okay, so if it's not converging to zeros, so n a sub n either converging to C positive or n a sub n converging is divergent, okay, to infinity. Okay, now what happened if this convergent to C? That implies if n a sub n convergent to something positive and finite, then you see it's a sub n, n times a sub n is a sub n over 1 over n, right? Okay, convergent to C. It means the series a sub n and the series 1 over n are both convergent or both divergent. But since this series is divergent by harmonic, then the series a sub n is divergent by limit comparison test. Okay, now actually the same argument applies, nearly applies, that if the n times a sub n actually convergent to infinity, means a sub n over 1 over n converges to infinity. Is it right? that implies that a sub n is greater than 1 over n for any n greater than some capital N for some n. How to say that? How to say that? Choose the ratio you want. Okay. You can always, if this ratio converges to infinity, it means there is let me don't go too fast. It means there is some number n. Okay. There is some number n such that for every n greater than the number, every sequence after that capital N, a sub n over 1 over n is greater than 1. Okay, but that means starting from that capital N, the sequence a sub n is already greater than 1, greater than 1 over n. So you have this series here, this series here. This is n equals to n to infinity. This is n equals to n to infinity. Therefore, the infinite sum from 1 to infinity is equals to the first couple terms of that a sub n plus this. But this is already divergent. By by comparison test, this will be divergent. Okay, now I don't want to go too far into this proofing thingy, but you better tell me now if there's any other question you want me to do from this 11.4 before I go to the next section. Now, if not, then your suggested homework from here will be from 11.4 will be from number 3 to number 31. I think that should be good enough. Number 38 is a good question that tickle you, supposed to be. Number 39, also a good one. That's proofing. Makes you think. How about number 44 also? Something to think about. Okay, but when I say something to think about, do your test first this Wednesday, and then during the weekend you think about this. Number 45, also a good one. Okay, that's for 11.4b. Let's see 11.5. 11.5 alternating series. A series definition. A series A sub n is alternating if the sequence A sub n is an alternating sequence. Okay, basically, these are the alternator. Okay, n Bn is positive term. Okay, so you will see that the sequence for A sub n will be either positive, then negative, then positive, then negative on, or the sequence A sub n start from negative and then positive and then negative and then positive and on. Okay, now from section 11.1, we learned that A sub n, absolute value of A sub n convergent to 0 implies the sequence is also convergent to 0. Okay. But if we say in this case, absolute of A sub n is equals to absolute of -1 to the n minus 1 B sub n, that will be just B sub n. Okay, the positive term, the positive part of that alternating sequence. Okay, so by divergence, by test of divergence, will it be the same if b to the n is negative? No, because b to the n is negative, then the absolute of that b to the b sub n will still be absolute of b sub n. See, absolute of something negative has to be positive. Right? Okay. The idea behind this A sub n, B sub n here, A sub n is alternating, but we try to isolate the positive term, the positive part of that alternating terms. See, so B sub n is actually the absolute of the sequence. Now, by test of divergence, we learn something. By test of divergence, we know that if the positive part of the series is not converging to 0, then the series of A sub n is divergent. Okay, the reason is because if the positive term of the series is not converging to 0, that implies a sub n also not converging to 0. By test of divergence, this is divergent. Does it make sense? Okay, so if you see the positive part of that alternating series already not converging to 0, then you just say, then of course you need to say a little bit, right? But basically you say, well, by test of divergence, the series as a whole will be divergent. Okay. Now we have alternating series tests. Next one, the alternating series test. Let a sub n equals to -1 to the n minus 1 b sub n. B sub n is positive. Okay, then if the positive part is decreasing down to 0, then the series for a sub n is convergent. And I can even say it is divergent, eventually divergent, convergent down to 0, eventually. I actually combine two things here. If you compare to our textbook, I combine two things. First one means b sub n plus 1 getting less than equals to b sub n for all n greater than certain n. It doesn't have to start from 1. That's why I use eventually. Okay, it is decreasing, eventually decreasing. And second part, that notation also means that b sub n is convergent to 0. Okay, so it is decreasing and convergent to 0. That's why I use this notation. Decreasing and convergent to 0. I put that E there to show that all you need is eventually. Okay, let's say starting from the 100 term, then it starts decreasing. Okay, the first couple terms may be increasing. So the first couple terms, the b sub n may be increasing, right? But as long as after some n, it is decreasing down to 0, then that's all we need. Okay, that's alternating series test. The proof. The proof. Okay, now suppose b sub n plus 1 is less than equals to b sub n for all n greater equals to capital N. Okay, so we have the series -1 to the n minus 1 from n equals to capital N to infinity of b sub n. Okay, let's suppose we start from the positive part. Because you may start from the positive term, maybe from negative term, suppose. Positive first. So we will have b sub n minus b sub n plus 1 plus b sub n plus 2 minus b sub n plus 3 and on. Okay, now take a look on this number line. Okay, let's say this is 0. This is b sub n. Okay, now b sub n minus 1 is less than, the next term has magnitude less than the current term. So when you subtract by that, it will fall here. This is b sub n minus b sub n plus 1. Okay. If I add b sub n plus 2, right? B sub n plus 2, notice that this the magnitude here is b sub n plus 1, right? Now b sub n plus 2 is shorter than that. B sub n plus 2 is shorter than that. Okay, now this point here will be b sub n minus b sub n plus 1 plus b sub n plus 2. Okay, now, so you will end up with the following situation. From 0, you add b sub n, you becomes here. You subtract by b sub n minus 1 and go this way, and then subtract and add, subtract, add, subtract, add, subtract. The more terms you take, the smaller the interval it can move. Eventually, it goes down to 0. Okay, let's use an example. Let's use an example. I try to give you the feeling of the proof. So if you want to see the formal proof, take a look in the book. Okay, now this is the intuitive proof. Suppose we deal with 1 over n. So 0, 1 over 1 is 1. Subtract 1 over 2 becomes 1/2, right? So this is 1 over 1. This is 1 over 1 minus 1/2. Okay, so notice that this is where you start. Okay, after the first term, you're here. Okay, now notice that the remaining term will always be in this interval between 0 to 1. In fact, after you get the second term, you add up to the second term, 1 minus 1/2, you get to here, right? Okay, so later on, you know that the infinite sum must be somewhere here. Okay, now if I add 1/3, 1/2 plus 1/3 is 5/6. That is 1 minus 1/2 plus 1/3. The sum up to the third term tells us that the infinite sum must be in this interval. Okay, so later on, if you subtract something, it will come here. You add something, it comes only up to here. Eventually, the interval gets smaller and smaller, and then it stops somewhere. The infinite sum basically will stop, quote unquote, stop somewhere. Okay, so that's the sketch of the proof. The formal proof, look at the book. Okay, my instructor actually, I remember when he explained it to us, is basically this: when you add or subtract by the next term, it has to be with the distance less than the one you add before. So from something you add here, but when you subtract by smaller distance. You subtract by smaller distance. You subtract by smaller distance. I mean, subtract by smaller distance, add by smaller distance, subtract by smaller distance, add by smaller distance. Eventually, this becomes very, very small that it cannot escape to anywhere but a certain point. Okay, so let's say this is S1, this is S2, this is S3, this is S4, this is S5, and on. Okay, in other words, if you start from the positive term, S1 will be the upper bound and S2 will be the lower bound. Okay, and later on you will have that S2 is the lower bound for S4, as lower bound for S6, while S1 is the upper bound for S3, is the upper bound for S5. Do you see what I mean? Okay, so you will see that the even partial sum is increasing, but the odd partial sum will be decreasing. Okay, this will increase, this will decrease. Eventually they meet at S, the infinite sum. Okay, that's the sketch of the proof. So you will see here that all we need to show is, to show that the alternating series test, an alternating series is convergent we only need to show that the absolute of the alternating sequence, which is the positive part, is decreasing. And it is decreasing to 0. Okay? At least eventually. That's all we need to show. We need to show it is decreasing down to 0. Okay, and better, even better, the error and the error is equal to, is less than the error after you add the first n terms is less than b sub n plus 1. Take a look here. Take a look here. From this diagram, let's say this is the infinite sum. Okay? Let's say that's the infinite sum. Notice that the error after you go up to the fifth term, the error after you get to the fifth term must be less than the error up to the fifth partial sum must be less than the sixth term. Maybe less than equals to. For our error analysis. Okay, with those said, we are ready to do problems. Let's see, for example, number 2. We have this series 2/3 minus 2/5 plus 2/7 minus 2/9. That is equals to the infinite series, n equals to 1 to infinity. We start from positive terms, so that's n minus 1, negative 1 to the n minus 1. The numerator is always 2. The denominator is linear, 2n plus 1. Right? Okay. Now, show that it is divergent or convergent. Solution. B sub n, the positive part, is 2/2n plus 1. How do we show that this is divergent? Convergent. We need to first claim that B sub n is decreasing. Proof. 2/2n plus 1 is greater than 2/2 times n plus 1 plus 1. Is it right? We want to show that B sub n, we want to show that B sub n is greater than B sub n plus 1. That's what we want to show. How do you show that? Well, we start from, of course, n plus 1 is greater than n, so 2n. If you multiply both sides by 2, the inequality is being maintained. If you add 1, the inequality is still being maintained. But when you do the reciprocal, since it is positive, when you do the reciprocal, the inequality is reversed. So we have shown that it is decreasing. Second, that Bn is convergent to 0. Okay, 2/2n plus 1. And this one is easy, right? It converges to 0. So by alternating series tests, this series -1 to the n minus 1 of 2/2n plus 1 is convergent. You just need to show that the positive part of the sequence is decreasing down to 0. That's all you need to show. That's for number 2. Let's see number 3. We have the series -2/5 plus 4/6 minus 6/7 plus 8/8 and on. This is the series, start from negative. So that's -1 to the n. On the top, it's always increasing by 2. The bottom increasing by 1. So the slope is 1. Okay, and the n start from 1. When n equals to 1, this 2, n equals to 2 is 4 and 6 and 8. The denominator When n equals to 1, that's 5. N equals to 2, it's 6. N equals to 3, that's 7. Okay, now then, how do we show this is convergent and divergent? Take a look on the limit. Bn is 2n over n plus 4, which is 2 over 1 plus 4 over n, which is convergent to 2. And that's not 0. Okay, now that implies a sub n, which is -1 to the n of Bn, is not convergent to 0 by test of divergence, test for divergence. The series is divergent. Number 7. We have the series from 1 to infinity of -1 to the n times 3n minus 1 over 2n plus 1. That's alternating, right? Okay, so how to show that's convergent or divergent? Take a look on the positive part. Notice that this is equal to 3 minus 1 over n over 2 plus 1 over n. And this is convergent to 3 over 2. Okay? In other words, a sub n, which is -1 to the n of Bn, is not convergent to 0. That's all we need, actually. That's all we need. Once it is not convergent, the positive term is not convergent to 0, that's end of story. Okay? This alternating series 3n minus 1 over 2n plus 1 is divergence. That's for number 7. Number 11. We have this series, this one more question, and then I take a break. -1 to n plus 1 of n squared over n cubed plus 4. Bn is equal to n squared over n cubed plus 4. Let me show that this is actually convergent to 0 first. Okay, divided by n squared. Divided by n squared. Actually, just divide by n squared. And this is divided by n squared. This will convergent to 0, right? Okay, so it is at least convergent. We need decreasing part. How do we show that it is decreasing? Claim Bn is decreasing. prove? How do you prove that? How do you prove B, in other words, B sub n is greater than B sub n plus 1? How do you prove that? How do you prove that this sequence of positive terms is divergent? You know what? I give you the idea, but I want you to write down the proof. Okay, use continuous superposition function. Okay, try to do that. Basically, then you create fx equals to x squared over x cubed plus 4. Okay, and then do the derivative. Show that this is negative. Okay, that's another 2 or 3 minutes from there, plus 10 minutes break. We come back at 9:15. Okay, let's continue again. So I want to erase these. So let fx equals to x squared over x cubed plus 4. And this function is continuous on 1 to infinity, right? Now the first derivative is that's 2x times x cubed plus 4 minus x squared times 3x squared, which is x cubed plus 4 being squared. This is 2x to the 4th plus 8x minus 3x to the 4th, which is 8x minus x to the 4th over x cubed plus 4 squared. Okay, now f prime x will be negative when 8x minus x to the 4th is less than 0. Is it right? And this is 8x is less than x to the 4th. Now, our x will be greater or equals to 1, right? Since x is greater or equals to 1, that's our limitation. So I can divide by a positive number. Okay, so fx is decreasing for x greater than 2. In other words, fx is eventually decreasing. Is it right? Okay, by continuous superposition function, then B sub n is eventually decreasing. Or you can say Bn is decreasing for n greater than 2. Okay, where you become more specific after what kind of number will the sequence, the positive term becomes decreasing. Okay, now once we show those, the positive term to be decreasing and it is convergent to 0. So by alternating series tests, the series is convergent. Okay, actually, before we go on further, there's one important alternating series that we need to discuss. We need to talk about alternating harmonic series. Alternating harmonic series. Is convergent. Okay, proof. Actually, the proof is quite easy. You see that the positive term b sub n is 1 over n, right? Okay, b sub n is decreasing. Proof. N is less than n plus 1, and at the same time is positive. So the reciprocal, you reverse the inequality, so b sub n is greater than b sub n plus 1. Okay, next, b sub n is convergent to 0, which is clear, right? 1 over n convergent to 0. So by alternating series tests, alternating harmonic series, I think alternating harmonic series, or you call that harmonic alternating series. I think alternating harmonic series is convergent. Okay, alternating harmonic series is convergent. Okay, now implicitly in this section, note, implicitly, this section requires you to look back to section 11.1, where you need to show a sequence is convergent. Okay. In this section, however, the sequence, in this case, the positive sequence Bn, needs to be convergent to 0. Okay, and decreasing, of course. But for the converging, the sequence that is convergent part, you need that to be convergent to 0. Okay, so if we look at number 19, I will do one more problem from this part, and then after this, I will do the estimation. the series -1 to the n times n to the n over n factorial. Is this series convergent or divergent? Well, we take a look on the positive term. Okay, now this is n times n times n times n all the way to n over n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. I wonder if you remember we did this one question before. And then we will rewrite this as n over n times n over n minus 1 times n over n minus 2 all the way to n over 2 to n over 1, which is greater equals to 1, 1, 1, 1, n. Okay, which is n. In other words, so Bn is greater equals to n, but that n converges to infinity. So the positive term Bn converges to infinity. Okay, by divergence theorem, test for divergence. This series, therefore, oh, I'm sorry. Yeah. So -1 to the n to the n over n factorial is divergent. Okay. Now let's do question like number 23. Show that this series from 1 to infinity of -1 to the n plus 1 over n to the 6 is convergent. And how many terms to add such that the error to the infinite sum is less than 0.00005. Okay, now look at the positive term. That's 1 over n to the 6. Okay, this is clearly convergent to 0. Okay, and because n is positive but less than n plus 1, actually I need to say that n is at least 1. Okay, then when you take it to the power to the 6, n plus 1 to the 6 is still greater. And then when you do the reciprocal, you reverse the inequality sign. So b sub n is greater than b sub n plus 1. Okay, so this series by alternating series theorem, alternating series test, what happened? This series is convergent. So once we know it is convergent, then we have a reason to ask how many terms to add such that the infinite sum to that partial sum has error less than 0.00005. But we have learned this, that the error up to the nth term is less than b sub n plus 1, right? Which we can set to be less than 0.00005. This is 1 over n plus 1 to the 6 is less than 5 over 100,000. Okay, if I do the reciprocal, n plus 1 to the 6 is greater than 20,000. Okay, now from here, just do trial and error. Just do trial and error. When n equals to 9, that's already way too big. We already have 10 to the 6, right? Which is 1 million. That's way too big, right? But at least we know that 9 terms will solve the problem. Now let's go lower from here. Try, let's say n equals to 7. So 8 to the 6 equals to what? Still a big number. That is still 20,000. Let's make it smaller. Well, let's say when n equals to 5. That's 46,000 something. How about when n equals to 4? See, honestly, I don't know the answer. So what I do is, you can also do the 6th root though. Okay, to properly solve that, n plus 1 is greater than the 6th root of 20,000, right? Okay, so 20,000 to the power of 1 over 6. That's, sorry, 20, I forgot the parentheses, to the power of 1 over 6. 5. This is 5 something. Okay, so n has to be greater than 4.21 something. So we can use n equals to 5. Use n equals to 5 to be enough. Okay, so when we add the first 5 terms only, the sum from 1 to 5 of -1 to the n plus 1 over n to the 6. Okay, this is equal to 1 minus 1 over 2 to the 6 plus 1 over 3 to the 6 minus 1 over 4 to the 6 plus, hold on. Yeah, and to the 6 plus 1 over 5 to the 6, up to 5 terms only. This will give us the error here, the sum as 5 here. Infinite sum to the 5th partial sum must be less than 0.00005. Okay, that's so you actually just look at the next term. The error must be less than the next term. Number 26. Infinite sum -1 to the n minus 1 of n(e) to the -n, and the error should be less than 0.01. We need to find how many terms, but first we need to show that it is convergent. So the positive term is n(e) to the -n. This is n over e to the n. How to show that this is decreasing and convergent to 0? I will use continuous superposition function. Fx is x over e to the x. That's continuous on one. Actually, continuous on all real numbers, but at least we know that it's continuous from 1 to infinity. Okay, and the first derivative is e to the x minus x e to the x over e to the 2x. Factor e to the x and cancel. I get 1 minus x over e to the x. Okay, that will be negative when 1 over x is less than 0. It happens that it is x is greater than 1. Okay, also that the limit I will use L'Hopital, right? That's 1 over e to the x, which is equals to 0. So by alternating series test, that series -1 to the n plus n minus 1 of n e to the -n is convergent. Now we want the error to be less than 0.01 according to that question. How many terms do we need? Well, just set that the next term to be less than that. Okay, so this will be n plus 1 e to the -n plus 1 less than 1 over 100. So 100 times n plus 1 is greater than e to the n plus 1. Can you solve for n? Can we solve? Instead of fully solve that, just find the n where this is satisfied. Okay, just find the n where this is satisfied. Okay, that's what I will do. That's what I plan to do. Let me check when, just to get a feeling. So when n equals to 10, will that work? So 100 times 11, is it less than e to the 11? E to the 11th is according to the computation, my calculator 59,000 already. Oh, that's really big, huh? And this is 1100. That's way too big. Make it smaller. Let's say n equals to 7. So 100 times 8 greater than e to the 8th. I think it is still true. In fact, yeah, e to the 8th is 2,800. It is still true. That's still true. What happens if n equals to 4? So 1,100 times 5 is it less than e to the 5th? No, it's not. So the number of terms must be more than 4, but less than 7. Okay, let's try n equals to 6. I'm sorry, this is e to the n plus 1, so it should be 7 here. E to the 7 is 1,000 something. Okay. So at least 6 terms will work. Will 5 terms work? No, 5 terms doesn't work. We just need 6 terms. So S6, which is the sum of the first 6 terms of -1 to the n minus 1 n times e to the negative n has error less than 0.01 from the actual sum. The actual infinite sum. Last one before we go, number 29. Approximate the sum to 4 decimal places. In other words, the error should be less than 0.0001. Okay, I will use the error to be I will use the error to be less than 0.00005 for rounding. Okay. For number 29, the series is -1 to the n minus 1 n squared over 10 to the n of n from 1 to infinity. I don't need to prove it is convergent or not anymore. I don't need to prove it is convergent or not anymore. I just need to show to find the sum, estimate the sum. Okay, but first I need to know how many terms I need to take. Okay, so the error should be less than n plus, should be less than b plus 1. I mean, sorry, b sub n plus 1. So n plus 1 squared over 10 to the n plus 1 should be less than 0.00005. Okay, let's do this kind of estimate. On the right hand side, that's 5 over 100,000. Okay, so you see that we need at least 5 terms, right? For n equals to 5, it is still not enough, trust me. It will be 6 squared over 10 to the 6, which is 36 over, 36 over 100,000, over 1 million. Oh, it already works. Yeah, it already works. Yeah, because this is 3.6 over 100,000, right? It's already less than that. Oh, wow, I guess it right. So n equals to 5 is good enough. We need 5 terms. Need S5. Okay, which is equals to, when n equals to 1, that's 1 over 10. When n equals to 2, that's 4 over 100. When n equals to 3, that's 9 over 1,000. 4, that's 16 over 10,000. 5, that's 25 over 100,000. Okay, so that's 0.1 minus 0.04 plus 0.009. I'm sorry, it should be minus and that should be plus. Minus 0.0016 plus 0.00025. Okay. Get this is 0.06765. Now suppose I see what is the next term, just for fun, The next term will be minus 30, why I don't, yeah, minus 36 over 1 million. That's minus 0.000036. If I include the red term, I will get 0.067614. Now let's see how accurate it is. 1, 2, 3, 4. 1, 2, 3, 4. The fifth decimal place is 5. And 1. Okay, so the error here is already less than, the error is already less than 0.000036. Okay, this is where I want to stop. We've done with 11.5. Suggested homework for 11.5 is from number 3 to number, I think up to number 29 is good enough. Okay, that's for today. See you then on Wednesday with your tests.